A chronon is a proposed quantum of time, that is, a discrete and indivisible unit of time as part of a hypothesis that proposes that time is not continuous. Early work. While time is a continuous quantity in both standard quantum mechanics and general relativity, many physicists have suggested that a discrete model of time might work, especially when considering the combination of quantum mechanics with general relativity to produce a theory of quantum gravity. The term was introduced in this sense by Robert Elliott VI in 1927, a quantum theory in which time is a quantum variable with a discrete spectrum, and which is nevertheless consistent with special relativity, was proposed by Chen-Ning Yang in 1947. Henry Margenau in 1950 suggested that the chronon might be the time for light to travel the classical radius of an electron. Work by Calderola. A prominent model was introduced by Piero Calderola in 1980. In Calderola's model, one chronon corresponds to about 6.27 times 10⁻24 seconds for an electron. This is much longer than the Planck time, which is only about 5.39 times 10 to 44 seconds. The Planck time is a theoretical lower bound on the length of time that could exist between two connected events. But it is not a quantization of time itself, since there is no requirement that the time between two events be separated by a discrete number of Planck times. For example, ordered pairs of events and could each be separated by slightly more than one Planck time. This would produce a measurement limit of 1 Planck time between A and B or B and C, but a limit of 3 Planck times between A and C. Additionally, the Planck time is a universal quantization of time itself, whereas the chronon is a quantization of the evolution in a system along its world line. Consequently, the value of the chronon, like other quantized observables in quantum mechanics, is a function of the system under consideration, particularly its boundary conditions. The value for the chronon, θ0, is calculated from this formula. It can be seen that the nature of the moving particle being considered must be specified, since the value of the chronon depends on the particle's charge and mass. Calderola claims the chronon has important implications for quantum mechanics. In particular, that it allows for a clear answer to the question of whether a free-falling charged particle does or does not emit radiation. This model supposedly avoids the difficulties met by Abraham Lorentz's and Dirac's approaches to the problem, and provides a natural explication of quantum decoherence.